Hey ladies and gentlemen, welcome back to another science lesson. We are going to be talking about transfer of heat. Don't forget you guys have some homework, temperature and heat homework in Schoology, and your big essay for energy in the news is due Friday. And we've got a new test coming up next week, probably going to happen on Tuesday. There's a review packet in your notes. Go ahead and get that done by Monday so your test can be Tuesday. Our question of the day is quite an interesting one because we talked about yesterday there being no such thing as cold energy. If there's no such thing as cold, then there's only the lack of heat. Now, the lack of all heat, the lack of all thermal energy is absolute zero. That's the lowest temperature that anything could be. Why? Because there'd be no molecular motion at all, no kinetic or thermal energy whatsoever. That ends up being negative 273 degrees Celsius, also known as 0 degrees Kelvin, absolute zero. But if there's a lower limit of temperature, is there an upper limit? In other words, how hot can something get? Let's take a look.
Hey, Vsauce, Michael here, and my tea is quite hot, but it's not the hottest thing in the universe. So what is? I mean, we know that there is an absolute zero, but is there an absolute hot? A point at which something is so hot it can't get any hotter? Well, to find out, let's begin with the human body. Your internal temperature is not constant. 37 degrees, 98.6, sure, but those are averages. Your body's internal temperature fluctuates by about 1 degree Fahrenheit, half a degree Celsius, throughout the day in a cycle. Assuming you sleep at night, at 4:30 in the morning, your body reaches its coolest, natural, healthy temperature, and at 7 p.m., it reaches its highest. But a dangerous fever is not good. 108 degrees Fahrenheit is almost always lethal. The highest recorded air temperature across all of Earth has happened 4 times in Death Valley, where it has reached 129 degrees Fahrenheit. 180 degrees Fahrenheit is the recommended temperature for water when brewing coffee, and at 210 degrees Fahrenheit, a cake is done. 2,000 degrees Fahrenheit is the temperature of lava fresh out of the ground. But come on, make your own lava like Green Science Pro. This guy uses Fresnel lenses to focus the sun's energy onto whatever he wants. This is a small piece of obsidian, volcanic glass, which he can melt into actual lava right in his backyard. Keep in mind that the sun is having that effect even though it is 93 million miles away from Earth. Right up on the surface of the sun is a different story. The surface clocks in at 10,000 degrees Fahrenheit, but the center, where fusion occurs, is ridiculous. Temperatures there reach 28 million degrees.
But is that the hottest it can get? Well, I'm going to link that in our video links so you can continue to see the hottest things in the universe. I highly recommend you go to the video links for all the excessive, wonderful videos for science. Hey guys, we're going to learn about transfer of heat today, so if you don't already have your notes packet out, find your energy note packet. We're going to continue on with transfer of heat notes. Now, there's 3 types of heat transfer that you guys are already familiar with. But first, let's talk about heat. Heat, the word, means the transfer of thermal energy. And thermal energy always transfers from high to low. In other words, diffuses from where there's a lot to where there's little. So hot things heat up cooler things. Now, this can happen in 3 ways: conduction, convection, or radiation. Let's take a closer look at each of those 3 words. Conduction is the heat transfer by touch. In other words, the materials have to either be touching, or we're talking about the individual molecules within the material itself. For example, a metal pan on a stove will conduct heat to your hand. And when you touch that pan, you will feel the heat being transferred from the bottom of the pan up through the metal to the handle. So what makes conduction happen? Well, the molecules of a solid are tending to be the ones that will do conduction because the molecules being closely together, packed together, as one vibrates, it will hit into another one and cause that one to vibrate, and so on down the line. Here's a piece of metal being heated by a flame. The hottest temperatures are here, but soon enough, those kinetic vibrations, those thermal energy, will transfer through the bar to this side. Let's take a look at what the molecules would look like in conduction.
So here we see two likely lads toasting some marshmallows on an open fire. One of them has chosen a metal rod to put their marshmallow on the end of. The other one chose a glass rod. Which one of them do you think is going to burn their hands on their rod first? Well, let's wait and see. Oh, there we go. We can see it was the guy with the metal rod. Why do we think that was? Well, actually, it's because metals are much better at conducting than glass. Glass still does conduct, just not as well. Let's zoom in and look at the particles in the glass and see how it conducts. So glass is a typical solid in the way it conducts. The particles by the fire start to gain heat from it and start to vibrate much more vigorously. They then collide with the particles next to them, passing on the energy, and slowly down the rows each particles vibrate more and more vigorously, passing on heat to the next one through collisions. So it progresses slowly through the glass. This is how conduction happens in most normal solids, and is why solids are so good at conducting, because the particles are so close together that they collide very often. If you imagine it with a liquid or with a gas, the particles are quite far apart, so they do still conduct, they can still collide, it's just not going to happen very often.
Great. So we've all experienced conduction. Try it now. Find a piece of metal, something that's been laying around. Maybe the chair you're sitting on has some metal legs or something, and grab that. What do you feel? Well, if you said it feels cold, then you're feeling reverse conduction. Remember, thermal energy always flows from high to low areas, so you're warmer than the chair, right? Well, if you're a living thing, you probably are. So the heat flows out of your hand towards the chair, and it's conducted away by the metal. Now, the way your nerves work, when heat conducts away from your body, you sense that as, you guessed it, cold. But there's no cold energy coming to you. That's just the heat leaving your body. Certain materials are better conductors than others. Metal is a great conductor. It transfers heat very easily. Insulators, on the other hand, are materials that have the property of not conducting heat. They're just made of different materials. If you remember our properties of matter unit, you probably remember the word conductor. So, oven mitts and big puffy coats are not good conductors. Why, air is a terrible conductor. So, most winter coats are basically 2 layers of fabric, some puffy material just to keep those layers spread out, and to trap the air within. The air is really what's being the insulator for your coat. I want you to keep this picture in mind. There's 2 ice cubes on some trays, because we're going to be looking at this in a future class when we talk about conductors and insulators. Next up, heat can transfer through liquids or through gases, and this is called convection, whereas conduction happens best through solids. Convection is when heat travels through fluids, which we call liquids and gases. Convection creates currents. And there's 2 things that are happening in convection. When a material is heated, it typically expands. Its volume increases. The molecules spread out. When this happens, the volume increases while the mass stays the same, and effectively reduces the density of the object. Objects with low densities float, you remember. So a hot air balloon is filled with hot air that's expanded, the volume's increased, but the mass is the same, and compared to air around it, it's less dense. So a hot air balloon will rise. Similarly, water will have the same effect. Now, molecules of air and water, as they move, they will have a little bit of attraction between other molecules of the same type. So as one molecule moves, it grabs onto the other molecules nearby, and it causes them to move as well. We get a current created here of air. Warm air rising. It reaches a point where it's up high in the atmosphere, and maybe it cools down. Cool air will sink. And you've got this flow, this pulling action that happens. It's called wind. That's a convection current. Similarly in water, where warm air rises and then falls. This could be in a pot of water or in an ocean or some other large body of water. You could test this out for yourself. Just get 2 jars of water, 1 warm, put red food coloring in that, and get a cold water and put blue. Pour your blue water carefully into the red water, and you'll notice that the blue colder water will sink, whereas the warmer red water will rise to the top. And they'll mix a little, but if you do it carefully, you can get the blue water to be on the bottom and the red on the top. Give it a try. Another example, of convection that you will see is convection currents within the Earth. Deep within the Earth, currents rise with magma and different parts of the mantle.
It happens because hot rock rises, heated by the Earth's core. Near the surface, the rock spreads in two directions and goes sideways. It begins to lose heat. Eventually, the much cooler rock sinks back down. Through this spreading process, the Earth's crust is very slowly dragged apart.
If you take a look at this picture, you can see a freeze frame of the convection current deep within the Earth, where the hot lava and magma and melted rocks are rising through the mantle, cooling and then sinking again. Of course, this may take hundreds and thousands of years for this movement to happen, but it's a convection current nonetheless. And our final transfer of thermal energy, if you will, is radiation, which you've probably heard of before. We talked about it as the transfer of energy through empty space. In this case, we're specifically looking at heat. Waves of energy travel without a material. This is how light and heat from our sun reach our planet. And within the electromagnetic spectrum, there's light, there's X-rays, gamma rays, and there are infrared. Infrared are the waves that carry heat. A radiator in your room will heat the room. And even if there was no air in the room, if we pulled all the air out with a vacuum, the radiator would still radiate heat. And that's how energy can travel through the emptiness of space.
Be transferred from place to place by conduction, convection, and radiation. Today, though, we'll be focusing on radiation. All objects emit and absorb infrared radiation. Even we do, just a very low amount, but it can still be picked up by thermal imaging cameras that detect the infrared radiation and convert it to visible light. The hotter an object is, the more radiation it emits. Some of it even becomes visible light that we can see. Infrared radiation is a type of electromagnetic radiation which has a lower frequency than light and involves waves rather than particles. This means that, unlike conduction and convection, radiation can even pass through the vacuum of space. This is why we can still feel the heat from the sun even though it's 150 million kilometers away from the Earth. Some surfaces are better than others at emitting and absorbing infrared radiation. Dark matte surfaces are good at emitting and absorbing infrared radiation, which is why solar panels are black in order to absorb the maximum amount of heat for your hot shower. White, light, shiny surfaces are poor at absorbing and emitting infrared radiation, but they are good reflectors, which is how a thermos works. If you want to keep your cup of tea hot all day, you put it in a thermos that is coated inside with a shiny surface to reflect the radiation back to the...
So, radiation occurs in the infrared scale of the electromagnetic spectrum. Radiation traveling in waves that can be measured by length of energy of waves, which brings us back to our original question. Can we say there's an upper limit of radiation? Well, it has to do with these wavelengths. How small can they get? Well, now that we've gone over the 3 types of heat transfer, let's take a quick look at that homework you guys have due for Wednesday. And I particularly would like to look at question number 2, because that's not a question you could have answered until today, because we haven't talked about heat transfer. Which type of heat transfer could be modeled or explained similarly to a bowling ball rolling down a lane and hitting a bunch of pins? What are we looking at here? Well, we're looking at the transfer of energy. Is this conduction, convection, or radiation? Look back at your definitions and think about what this example best models. Is it conduction, convection, or radiation? Here's question 1. Remember, the key word here is thermal energy. Please explain in terms of thermal energy, which means you probably want to restate a definition of why a bottle of soda in the sun has more thermal energy than the one in the cooler of ice. What does that mean for its molecules? What does it mean for the molecules? And why does your hand feel cold if you spill water on it, even though the water's at room temperature? Remember, when water or any other material touches another material, the energy flows from high to low. And finally, the thermal energy in a campfire compared to the thermal energy in a frozen lake. Lakes are large, folks. Campfires, although they're hot, are small. That's enough clues for that. Hey guys, pick 3 of the 4 that you can answer the best in complete sentences. Explain, explain, explain. I need to know that you know the things. Hey guys, thanks so much. Remember, convection, conduction, and radiation are all things you've probably already experienced in your life and know plenty about. But if you hadn't ever heard of those things, well, now you know. Hey, thanks for joining us, and I'll see you on the next one. Thanks for trying science. Bye.